Welcome to this RF Industry Icon podcast. I'm Pat Hindle, and today I'm talking with Shahriar Shahramian, head of Bell Labs ASICs and Packaging Research Lab, Bell Labs Fellow, Adjunct Professor at Columbia University, and founder of the Signal Path. Welcome, Shahriar.
Thank you so much for having me.
So you're an accomplished technical leader and well-known influencer on YouTube in the industry. So I'm happy to have you on this RF Industry Icon podcast today. And I thought I'd just kind of start at the beginning. You graduated from University of Toronto with a PhD in electrical engineering. And I kind of want to know, what steered you in that direction? Where did your interest in electronics develop?
No, so thanks, Pat, for the introduction. I would like to claim that this was some kind of a great insight and foresight on how I chose my career path. As with most things in life, there's quite a bit of coincidences and randomness that certainly comes into it. I actually did my undergraduate degree in computer engineering, which is not related directly to electronics. And after I finished my undergraduate, I shifted towards electronics. I've always had a passion for it. And then I ended up doing my PhD in electrical engineering. And I did find this combination to be really useful. And I've come to recommend it to people who want to do graduate studies, because having this ability to do some programming and understand computer architecture and understand how to deal with code is more and more relevant, perhaps more than it's ever been. So even in our field, having that diverse background has been extremely helpful. I know that it's somewhat an unusual thing because it puts a lot of pressure towards the end of your computer engineering degree to all of a sudden shift to electronics. But I think it was a worthwhile thing. Like I said, it was an accident, but it's been quite good. Electronics certainly been a passion of mine since I was maybe even 5 or 6 years old. I had great influences. My uncles were a big influence. They were always tinkering with something. And that through both genetics and environment has, I think, led into where I am today.
Well, yeah, that's a good point. I feel like some people get too focused on one area, and with all the, computing power now is just so powerful, AI, machine learning, it kind of all is tying together and making it more software driven.
Yeah, I think perhaps every generation says this, but we have lived through a very unusual set of transitions. I lived through the birth of Google and the birth of social media and the birth of YouTube. And this explosion of access. It wasn't there when I was in high school. Not to mention that, anyway, I wasn't even living in North America at the time when I was younger. But sitting at those transition points is very different than being born into it. And in a way, we're lucky because when you are at that transition, you seem to take some of the best of those experiences without those things with you and perhaps take the most out of it. And I feel like that's what's going on with AI too. And that is going to be a whole other experience. I play with and use ChatGPT quite regularly and interact with it and see some of the crazy things it does and some of the extraordinary things it does. And when I talk to it and I try to extract some information from it, it's always interesting that I can tell whether it's wrong or not because I have some background, I have some intuition, I have some experience. So I know whether the information I'm getting needs adjusted. And every time it makes a mistake, I just simply say, I think you're wrong about this. And it always apologizes, very polite. It's like, oh, I'm so sorry. Let me go back. But the critical thing is that if you don't know that it is wrong in some ways, you may never ask. And you fall into this very serious problem of not knowing that you don't know. And that's a big barrier to learning. And so these tools have to come with precautions on the user side. That there has to be an additional aspect to our education to prepare us for this fact, the fact that these tools are there and they're not completely settled yet, so we don't set ourselves in the wrong path. I think our education system will have to adjust pretty quickly, and a whole bunch of new learning skills for people in high school has to be brought in. But that's the kind of the cool thing about sitting at this edge of these transitions, and I'm sure, I said, every generation feels that way. There does seem to be something different about this generation. Exponential things do tend to give you that impression.
Yeah, for sure. So after graduating, you got a job at Nokia Bell Labs, where you are now. I guess you've been there close to 15 years, I think. So can you tell us about your first position there and then kind of how your current position you progressed along to be the head of the research lab there?
Yeah, I actually started as an intern at Bell Labs. This was quite a while ago, 2008, I think it was around that time. And I did my internship in IC design at Bell Labs. There was a visiting employee at the time, my old boss, Dr. Yves Byens. He came over to University of Toronto as an external for a PhD defense. And we made that connection, and I went into the organization, did my internship, and then from there became an MTS afterwards, and then grew my career over time. But labs is a unique place. People tend to stay there for a long time, and people tend to have decades, multi-decade careers at that place, and be able to have this multidisciplinary experience. In a way, it's kind of bittersweet because there are not that many places like the labs left in the industry where you have this quasi-freedom to do what you want and explore topics that perhaps aren't necessarily immediately connected to something you can make a product today. There are a few places like that in IBM. TJ Watson and Labs has some of that. TI has some of that. ADI has some of that. Intel certainly. But there's not that many. As the economy of the semiconductor industry and general tech has changed so much, that to be able to find these unique places to work is still definitely a privilege. And I'm quite fortunate to be able to continue doing what I do with this. And then eventually I created a lab, which is the RFIC Research and Packaging Lab at Bell Labs, where I lead a team of some very smart and motivated PhDs and researchers who work on these systems, trying to create the next generation of telecom devices and sensing devices. Now, as I said, the field is mature. So a lot of what we do, you can't say I'm going to do research and IC design for 10 years from now. It's just too long, right? The field is so much more established. Unless you're working on some bizarre nanosheet at DSMC where you're looking 10 years down the road, you're really working at things that have to become something real in a few years, which is where we are. Everything we work on has to become a product or something viable. So there's a lot of engineering, industrialization processes, new packaging and platforms. Everything is at a much higher layer in terms of complexity. Making individual ICs is just not enough in the industry to make an impact. So everything is at a module level, at a system level, and even at that application level. So Bell Labs having this multidisciplinary, diverse set of researchers really does help, because it means that I can go almost anywhere to any expertise I want inside of Bell Labs and have a chat about a field completely adjacent to mine, just so I can make sure that this thing actually works together, and talk with our customers at Nokia and generally globally to see who is going to use these devices. So it's a rare opportunity, and I hope that I can continue it for a while.
Yeah, I followed a lot of your publications. You're doing some really cool stuff. So I think one of the things I was most interested in is your radio on glass, because that seems to be like the next evolution in communications technology, perhaps a solution for sub-terahertz and 6G and maybe beyond that. So you can tell us a little bit about your work in that area.
Yeah, I mean, if you look at the industry as a whole again and step back, packaging in general is probably one of the most important aspects of the semiconductor industry. Is the thing that will likely enable us to go beyond this micro level of Moore's law into a macro layer, where we're talking about how do you put 1 trillion transistors together, right? Today we actually can't do that, and it's purely a problem of yield and economy. And we can probably put 100 million transistors together in a 3 nanometer, 2 nanometer process, but then you hit this really difficult yield that just simply doesn't allow you to grow the die any further. I mean, you can do it for niche applications, but for really anything that has a reasonable economy, you can. So all of a sudden, packaging has become this significant thing, as it's the only way to interconnect chips. But the problem with packaging has always been the same. Simply put, every time you slice a chip into digital chip, for example, you have to spend some additional power, some additional area, and some penalty for that split, because you need to communicate with them. But you cannot do that at the package level at the same lithography, at the same spacing and resolution you do inside the chip. So that means that you need a whole other packaging solution, and people are working on that on chiplets and high performance computes. That's kind of been established. And if you listen to some of the work that TSMC, for example, talks about, they go into details of how they think this would evolve on the digital side. Now, similarly, when you talk about analog and mixed signal, you have a different set of problems. If you want to make any practical, industrializable sub-terahertz modules that can actually be deployed realistically, you also need to solve a packaging problem there, because getting signals in and out of the chip at 200 gigahertz without losing so much of it that makes the whole system just generally impractical is a critical problem in sub-terahertz devices. So when we looked at building these D-band communication components, we can make it the IC. That's almost a solved problem. It's not easy, but it's not a very difficult problem anymore. You have silicon germanium devices with extraordinarily high performance, 500 gigahertz FDF max devices that are going to be coming out. So I can make you a D-band amplifier. But how do you connect that to the rest of your system without losing 60 VM and a quarter of a power left after you're done? Well, you need a new package. And this radio on glass architecture that we've been working on is essentially a way of slicing sub-terahertz devices with such that the interconnects are extremely low loss. They support the lithography needed at these very high frequencies. They're compatible with other industrial processes, so you can actually put a system together around it. And it has the economy, the cost would be reasonable so that you can deploy these. There's a unusual duality with terahertz circuits in general, or with communication devices. The free space path loss for the size of the antennas is a lot more at 200 gigahertz than it is at 20 gigahertz, which means if I build a network, any kind of network, at 200 gigahertz, I'm going to need more devices and I'm going to need more sites to connect everything because the link budget is less. So which means the cost per unit would actually have to be better than the cost per unit on lower frequencies because you need more of them. You can't say I'm going to build a network that needs 10 times as many devices and each of those devices costs 10 times as much. It just simply doesn't meet the economy. So a lot of what you see us discussing on our glass platform, our Radeon glass devices and modules and components we're demonstrating is an avenue for industrializing a practical solution. So you can actually build anything reasonable. But there's a caveat there. I want to make sure that there's no confusion. Sub-terahertz is not a mobility frequency, at least not anytime soon. Let's get the millimeter wave working before we talk about sub-terahertz for mobility. But for point-to-point links and very high data rate links over the air for these kind of specific backhaul applications is indeed a very attractive solution and it just adds to the rest of the spectrum, right? It doesn't replace anything. We built backhaul devices from 8 gigahertz to 170 gigahertz, each of them with a different deployment scenario, with a different set of requirements, different spectral efficiencies, and so on. But it's all about having this big portfolio of devices. So overall, for building anything in near terahertz, you have to make the economy work. Otherwise, it's just a science experiment in the lab. You can make one of anything, but whether you can, make a product out of it and deploy it, that's a whole other story.
Yeah, that's a good comment about terahertz frequencies, because I thought with 5G that millimeter wave would be really prolific, but it's only been minimally deployed. So I think we say we need to do that first, and then we can move on.
Yeah, certainly I think it's going to grow over time. There's no question. But as an industry, I think overall, everybody went after the hardest problem of millimeter wave. And the hardest problem of millimeter wave is handsets, right? It's got the most difficult link budget. It's got the most uncertain channel characteristic. It's got the worst antenna placement with respect to how you hold your phone. Everything is the hardest, right? Even the case of millimeter wave to your car is a significantly simpler problem than millimeter wave to your handset, just because you're not sitting in front of the car antenna. It can be on the roof of your car, or fixed wireless access, for example, being another deployment potential scenario which people are talking about. So perhaps some of that will happen over time. It's unclear, but nobody wants to make those kind of mistakes again in sub-terahertz, right? So you want to make sure that you deploy things for the right reason in the right places. There's also this entire avenue for sub-terahertz for sensing and radars and next generation high resolution devices. That I'm sure will happen as well. It's not communication related directly, but it's also an area of interest, I think.
So you have published a lot of work in high frequency and high speed IC designs, and I picked out the Radeon glass as my most interesting, but what do you consider some of the most important work that you're doing or other people are doing in the industry?
So there's been a lot of interest at D-band, as you know, between 110 to 170. Some people talk about it being a 6G technology. And these generational mobility things have become a bit confused, because when we talk about, or at least when Nokia talks about, when we say 6G, it's not just about technology to handsets. 6G actually encompasses a really complex network and a very complex interplay between network components. You cannot upgrade one part of your network alone, right? It just doesn't work. So if I say here's 10 times capacity for your mobility, okay, well, I have to increase my capacity for my fiber interfaces, my fixed network interfaces. All of that needs to also go up because the data needs to come from somewhere and go somewhere. So the network overall grows together. Every aspect of it needs to be upgraded. And I think Nokia is in a unique position in the industry because it's one of the very, very few places, if not the only company that actually covers almost every part of the communication infrastructure. Wireless, we have our mobile network division. So wireless, there's a lot of work there. There's fiber, obviously, Nokia has a huge presence in coherent optics communication. There is fixed network communication. So there's a lot of things that Nokia has to interconnect. So if you step back and look at all of Nokia's products at the same time, and we can think about how to optimize the network at that grand scheme. So when we talk about 6G, we're talking about that big, big picture. For us, looking at sub-terahertz devices and this high frequency, I think that the work that we've done in the past few years showing the practical industrialization of subtitles is probably one of the more significant things we've done recently, because that's, in my view, the part that makes the big differences. You could make subtitler circuits when I was a student, right? I remember seeing people showing modules that were operating at 150 gigahertz when I was even doing my PhD, but that is not something you could industrialize. Right? It was an experiment showing almost like a scientific demonstration. But here we're like, we don't want to make anything unless you can mass produce it. And that's a whole other engineering problem that I think we're making a big contribution to, among many other intelligent and clever people around the world who are working on these problems. As a whole, as a scientific community, I think these are pretty important.
And so you're a founder and host of the very popular blog YouTube series, The Signal Path. So I wanted to really know, how did you first start that? How did you form that idea and make it so successful? And, what were some of the obstacles? Because I think you have well over 100,000 followers now.
Yeah, 100,000 followers in the scheme of YouTube is in the noise floor of YouTube. But for such an esoteric set of topics, I'm glad that the audience finds it helpful and useful. And it started just because I wanted to have a way of giving back to the community. I found a lot of these concepts, especially microwave and millimeter wave circuits and systems and instrumentation, a lot of these things are often dealt with like black boxes. And there's a certain mystery and confusion about how they work. And in particular about the instrumentation, being involved in IEEE and being involved in education, if you look at a piece, let's say we get a paper and want to review that paper, right? We're in a conference. We can verify almost everything in that paper. We can look at the theory, we can look at the schematics, we can look and see if it makes sense, the block diagram. The only part where we really have to take for granted is the measurement, right? Because the measurement is what the authors say, this is what I measured. And if it's wrong because of the lack of familiarity of the students with the instrumentation, or as things get more complicated, these measurements are more complicated. And metrology is a very difficult field. So I wanted to bring that out a little bit more so that people actually understand, first of all, how this equipment work, because if you don't know how it works, you cannot use it effectively. You certainly don't know its limitations. So that's how it started. I said, let me focus on advanced metrology, instrumentation, and take things apart, show people how they work, and excite a certain level of passion into the genius that goes into how these things were made. You can open any piece of instrumentation, and at any given time, there may be like 7 or 8 Nobel Prizes in that box, right? That has led to it be what it is. It's not something to be taken lightly. We really do stand on the shoulders of giants when it comes to these things. So I wanted to bring that to the masses. And so as a result, it's very niche. It's very esoteric. Very few people find it interesting. But I think that the people who do find it interesting, hopefully have gotten value out of it. And of course, it allows me to play around with these things, which is a hobby and a passion of mine too. So why not share that with the world?
Well, I have to say what's most intriguing is you're just so natural about it. I love when you just take apart a PCB board and you just start pointing to components and saying, this does this function, then it goes into this function. And it just looks so natural that it's easy to follow. So I find that definitely intriguing. So what is your most popular episode, and why do you think it was a big hit?
Well, no, unsurprisingly, the thing that people find the most people watch are actually the things that are perhaps more introductory. I think perhaps one of my most viewed videos might be something in a Class AB amplifier. It's the reason it's viewed so much is because pretty much any undergraduate student in electrical engineering has to learn about that. So they search it, they find it, and hopefully they get some value out of it. And so views are actually not necessarily a good indication of interest in a particular video, because you can open a video and then close it immediately, and that's a view, but that's not attention, right? So the statistic that I find most extraordinary is how many minutes or how many hours the videos have been watched in total, right? And this is the extraordinary power of YouTube. And I just did a statistic a few weeks ago, just out of curiosity. So in my channel, even though it's a tiny channel, the total amount of watched hours on the channel is 200 years, right? It's 2 centuries, right?
Wow.
2 centuries it's 2 centuries worth of human consciousness listening to me blabble on about some bizarre, this is an amazing thing, just to think about it. And I said this going back to the network for a moment. If you look at when the pandemic happened, we were so concerned about our medical industries and our hospitals breaking down, because of being overloaded, not being designed to handle the shift and the need of the people to jump on them. And it happened in many places, and people were doing everything they can to avoid that. But nobody, or very few people, talked about the fact that our global communication infrastructure, the use of it, shifted almost overnight, right? We completely changed the way we consume data. We completely changed the way we interact with our network, and it just worked, right? If that pandemic had happened a decade earlier, it would have crippled internationally our commerce, right? Because now all the work from home that we take so seemingly, and there's some really cool plots showing how the traffic in the network shifted almost overnight from mobility, outdoor use to all indoor, all Wi-Fi, all through the fiber and copper that comes into your home. Everything changed, and it just worked, right? And that's a miracle of engineering, and we should not take it for granted. And just a decade of difference would have been a catastrophe. Not that the pandemic wasn't a catastrophe, but it could have been much, much worse. So I think that hopefully excited some passion for people to realize the importance of this engineering. As things become more common, they lose their awe. And when the awe and the magic is gone, we all lose, because it's the awe, the uncertainty, the dwelling in the obscurities is what brings a lot of curiosity into the domain you want to invest in. And if we lose that, if you take our cell phone and not recognize that there isn't even, I could take the 10 people in the world and put them in one room, and those 10 people could not hold in their brain the entire complexity of an iPhone, right? They cannot. It's just impossible, because there's so much engineering, from IC design and software and material and radio and AI, you just name it. The list goes on and on and on. And this complexity is not the first time we've made something that a group of people can't explain end to end, but it's the first time I think that thing is in everyone's pocket. And with that, I think that loss of passion about it, that's the part I'm trying to partially address with the YouTube channel. I don't want the magic to be lost, because it's there, and we need to appreciate it, and we need to love the fact that it is at our fingertips, so that we don't take it for granted. And it goes back to what you were saying, what is interesting in a channel, who watches it, and how. So I try to make it as easy as possible without it just becoming eye candy, right? A lot of videos on YouTube are basically eye candy. Somebody comes and does something, and your brain rewards you for watching someone's accomplishment, but actually you're not learning anything, right? It's like watching somebody perform an incredible athletic feat, right? It's fun to watch, but you're not becoming a better athlete by watching that. Maybe marginally, but not really significantly. And I think it's the same thing here. Learning is hard, right? Your brain has to, in a way, suffer for it to absorb this information. It's just an unfortunate reality of our biology. So I'm trying to not make things that are eye candy. I try not to be verbose on the videos that I make. That every sentence has to count for something. And hopefully this is recognized by the people. I think it is by those who really love the channel and enjoy the content. And I hope that I can do this for many more years.
No, it's absolutely recognized. I think the thing I find interesting about it is all your videos, because they're educational, they're very long format, very in depth, which is rare these days. Most videos are, they say, oh, you got to keep it short, 3 minutes, 5 minutes. And, yours are a good 45 minutes to an hour in depth, so that you do learn something.
Yeah, and the popularity of platforms like TikTok and YouTube Shorts and Instagram and so on is testament to the fact that we are fighting an uphill battle. The human brain wants these quick rewards, and these quick rewards are 30 seconds, 1 minute at a time. And as you said, you post a video that's 45 minutes long. Who's going to watch a 45-minute video, right? And yeah, 99.99% of the people won't, because it's hard to devote yourself to learning for 45 minutes. It is very hard. So I try to make it as interesting as I can, but we should ask ourselves as a society, what do we want to be the role model for our youth? How do you want to give the youth TikToks and Instagrams and all that, while simultaneously telling them that the actual real value is in the long form learning, right? And I think I said that in one of my recent videos. I said, look, the most valuable, non-renewable resource that you have as a human being is attention. That is your most valuable resource. And every time you spend that, and I'm not suggesting that your attention has to be every moment constructive, and productive. That's also not possible. But it can't be never productive. And I do worry because these are habits that you built very early on. And going back to what I said, when we're on the transition of a technology is very different because we can see both sides of it. But when you're born into it, it's a much harder battle. So I hope we can solve this as a species. We're all basically being experimented on in this massive social experiment without our consent, right? It's just happening. So we have to watch out for it. That is perhaps something I'm genuinely worried about.
Well, you're obviously a natural instructor and teacher, and you're an adjunct professor at Columbia University. What do you teach there, and, how are you involved in the university?
Yeah, I've been teaching it for some time, although my schedule is getting very difficult to continue that as I used to, but I only really teach one course a year anyway. But I was teaching a course on analog circuit design for some time, and then in the past few years, I was teaching another course, which is the kind of the art of RF measurement. It's RF measurement techniques. It's all about, similar to what I do on the channel, showing students, why is it that you measure something? Why are those parameters, the metrics that everybody measures? Why is everybody measuring noise figure? How do we agree on that? And how do you measure them? And importantly, how does the instrument measure it? How is this instrument measuring noise figure for you? And if you know that combination, you can tell if your measurement is right or wrong. So we spend a lot of time trying to figure out, well, how can I tell if my measurement is right? What do I change in my setup to convince myself that what I'm actually doing is right? And a simple example, you're measuring a noise figure of another LNA, right? And the instrument says the noise figure of this LNA is 3 dB. I'm like, okay, it's just a 20 dB gain, 3 dB noise figure. Is that right? How can I find out? Well, there's a lot of things you can do. You can add an attenuator before the LNA. The noise figure should go up by the attenuation. You take that attenuator, you add it after the LNA, but it has to go up by the freeze equation. But if it doesn't do that, then something is wrong. Again, you need to remeasure and figure out what's going on. Like even basic things like that opens the student's mind on how these are being done. And I think that hopefully, that's something that hopefully they can keep with them for their entire career. And that sense of examining their setup and being critical and everything. I mean, that's science. So hopefully that stays with them and they can learn from that. But that's what the course is about. Looking at every instrumentation, looking at how it works, how do you measure it, how do you leverage it. That's what it is. But there is some challenge with actually teaching in person because I could take the same number of hours that I spent and I could dedicate it and making a video, right? So I could reach 20 students or I could reach 20,000 students. Like, what is the best use of the time? And that's something that I do struggle with. I understand that being in person, of course, is different because in person, you can make a connection you just simply cannot make over the screen. But that is something. Anyway, I'm struggling with that. I haven't made up my mind of what makes sense or not. But teaching and education is I think that that's one of the most important things you can do with your life is to leave behind something in the conscious fabric of other people from how you thought about the world so that they can take that, improve it, enhance it, and pass it on, pass it forward. It's certainly one of my most fun pastimes.
I know you do a lot of activities. You're involved in a lot, including the IEEE. What are some of the things you're doing with IEEE?
Yeah, I think, being involved in IEEE is obviously quite important because you stay in touch with all the other researchers. You see the latest papers come in. I'm involved in a couple of the committees at IEEE in RFIC and ISSC, and it's a lot of work. And it's also very important that the people there really want to do this because you are shaping, first of all, the outcome of people's publications because you're evaluating them, judging them, and scoring them, and figuring out if the committee decides, okay, this paper gets in or doesn't get in. But also you can see the trends of how things change. And I think that IEEE probably will have to have some changes as the time passes because the systems we make and the ICs we make are so complex. And there's only so many circuit topologies that are actually useful, right? So just like any complex system, it can be anything. As soon as you put a selection criteria on a complex system, it would evolve in a certain direction. And if you're not careful, your selection criteria can evolve your system in a direction you don't want it to go, right? A famous example of that is with journalism, right? We put the selection criteria of journalism to be how many people click on the article because it's ad-driven, right? So you have how many people click on it, how many ads loads, how many people actually buy something from those ads. So that's the selection mechanism. And what did that do to journalism? well, it pushed it to clickbait titles, exaggerated titles, and just made the whole thing so much more difficult to navigate. This is not a well-established reality of journalism in general, which is an unfortunate thing. This can happen to any complicated system, depending on the criteria selection we put on it. Now, for IEEE and our papers, we need to make sure that the students, there's two things. Industry publishes the papers at these conferences because it's the latest and the greatest things they have created. They want to say, look, this is the state of the art. This is what can be done. And then universities do the same thing for a few different reasons. One is that they come up with something new, something unique, something that has a lot of potential. They want to publish that. But also they're trying to educate students, right? So the students, you used to be able to write a paper on a power amplifier at LNA and get it published. But now everything is so complex. You need to build a complicated system. And it's tough for students to all do all of that in the process of their degree. So I think one way to avoid this and one way to help the students is to just create sessions in conferences that you write papers that on circuits that didn't work, right? We don't do that today. But I would love to go to a conference and have a session, and the session is, here's 20 papers or 10 papers, none of these papers worked. But we measured them, they all didn't work. And here's why they didn't work. Like we made it because we thought it would work. This was our simulation. This is what we got as a measurement. This is what we found out was wrong, but it does not do what we wanted to do. We have to do it again. I mean, that carries so much value, but nobody does this because we don't have that environment set up. That's not the expectation people have when they submit the paper. And I hope this would change over time because I am, at least my intuition is that a session on papers that didn't work with the solution being figured out would be pretty well attended.
Yeah, you learn from your mistakes. Sometimes that's the best way. So that's a good idea. We do the same thing in Microwave Journal. We're looking for things that are new or unique so that they, it's something that adds to the knowledge base. But you're right. Learning from mistakes or doing, just 101 courses is much more valuable in some cases.
Yes. No, yeah, this is, and also I think the students will then would also find value in the sharing of their learning. And it would also build, hopefully, in their mind, the investigative style required in science to find a problem. Because if hey, my circuit didn't work, if I find out why it didn't work and build a foundation, analytical foundation around the problem, I can publish that. And that can be itself a driving force to bring some of this stuff forward to audiences. And I certainly would love to see that. We have quite a few of those examples in my own past where I've made something that didn't work and I found out why it didn't work. And I see that mistake repeated. Like I see other people having made that mistake. And it's just painful because every time somebody makes the same mistake you made, that's a waste of resources among everybody, right?
And so I really wanted to finish up with kind of your, what you see in the future coming. What are you most excited about with the future of communications, 6G and even beyond 6G? What do you see coming?
Well, right now, all you hear is obviously AI. And that's now whether how big the AI bubble actually is or if it's a bubble, it remains to be seen. The majority of the work in AI right now hasn't had the return on investment yet, right? People are trying to figure out where do we apply this extraordinary product of our genius and hopefully in the right places. And I think in the semiconductor industry, perhaps some of these will find themselves into some of the tools that we use on a day-to-day basis for circuit design. Just like anything else, you give me a good tool that can aid and assist in IC design, in co-packaging, in integration, in layout of very high frequency, which is an art in itself, then that would be great. It can accelerate how fast we can design it if it has a return on investment and economy model behind it built in. I think the high-performance compute platforms that are going to come in, some of these AI changes would certainly be interesting. My main concern isn't so much about the technology, it's actually about its utility and who owns it and how it's deployed. I have technology, as people say, it's not inherently good or bad, right? It's deployment, it's ownership, it's respect of privacy and respect for confidentiality and all of that. A lot of the models that we have used to create free platforms have been very much advertisement oriented. So I'm a bit concerned about that. There's all this drama now about how Microsoft is doing its AI built in and so on that you can, I'm sure, read about online. But if I'm going to be optimistic and think that things will work for the best, we will reach a point where I feel that we could think at an entirely new level of abstraction. And software people already enjoy this, by the way. Software has levels of abstraction that hardware couldn't even dream of today. You can develop and work with AI apps and look at creating all these models with having almost no knowledge of the underlying complexity. You don't need to know compilers, you don't need to know database structures, you don't need to know computer architecture, even a real programming language. You don't need to know any of this computer science background to get something done. There are people who obviously know all that, but that doesn't quite exist in our field, right? No matter how much we push the state of the art forward, when I want to teach a student electronics, I still have to start from a single transistor. It doesn't matter, right? Because that abstraction is not there. So perhaps some of that abstraction will find its way into our tools, allowing us to take it a level higher. That has its own negative consequences, but let's put that aside. And then that can actually have a pretty big impact. We can think about IC design and complex components and mixed signal in the same way we think about writing complex libraries in software. And that abstraction will be certainly very interesting. And it would probably find its way. That's going to be an interesting change. And in general, seeing what happens in these packaging platforms and how do we shift from growing our ICs larger, more transistors into a more chiplet-oriented, more distributed systems. And that has a cascading effect in all the software and everything that goes with it. It's certainly an interesting thing. All the work that we're doing in self-driving cars, potentially coming in with all the new radars that are required, all this automation, electric vehicle revolution that's happening, that's interesting, has, again, a huge semiconductor industry implication across many, many devices. The advances in 3.5 devices and their integration with silicon is now accelerating thanks to some of the other industries that are coming in, like, the white LED industry exploded the GaN market, because of the cheap substrate and all that. There's all these really cool interconnects. But I leave one thing that I think I think about a lot. We just recently had at Bell Labs the 10th Nobel Prize celebration. It was a 10th Nobel Prize associated to Bell Labs, which was for quantum dots. And in there was a slide that he was showing, talking about what he learned from his career. And one line in it was, a problem that may be very solved in your area might be very easy in another, right? And I think some of this complex interplay between different domains of knowledge may become more accessible with these AI tools who have this broad perspective. And you could borrow knowledge from other fields. If you go and talk to a biomedical student or a biomedical researcher, the problem they have with their electronics may seem trivial to somebody who's doing mixed signal IC design in our area, right? Because that knowledge is not cross-referenced so well. And I think some of this I'm very excited to discover as these tools become better and better. Again, being very optimistic that they're deployed well and ethically and all that, that can be a really big influence on a lot of areas we work on, not just electronics.
Well, great. Thank you so much, Shahriar, for sharing all your insights and stories with me today. They've been great. I've learned a lot. You're definitely an RF industry icon, and it's a pleasure talking with you today. For our listeners, you can find more podcasts at podcast.microjournal.com. Thanks for listening.